So welcome back. So with that being said, let's look at let's make it a bit more interesting. So let's remember our non-uniform fields. And so I can do a whole variety of things at this point. And I'm going to kind of follow the book because we've laid the basic foundation now. So then let's imagine we have what kind of charge would this be? It's going to be the arrows are going towards it. Yeah, you roll into a hole, so it's negative, yeah. So we have the field lines going in. This is like, oh, I'm sorry, this is not electric field, this is G, so it's a mass. And we imagine we can have another boulder moving from that altitude to that altitude. So the first thing to realize is it doesn't matter. The sideways stuff doesn't matter. All that matters is the change in altitude. So I can say, well, whereas before I said if you want to go from gravitational force to gravitational potential energy change, you multiply by the distance. Because the field is not uniform, as you go to different altitudes, the field lines are further away, which means there's less field. If there's less field, there's less force. So that means that you have less weight. So this force is changing as I go to different altitudes. And so I have to say, well, it's not F times the displacement. It's the integral of F with respect to the displacement. So I've got to do an integration. That's the only difference, really. And the same thing, by the way, goes from the gravitational field to the gravitational potential. I just integrate with respect to displacement rather than multiplying by the displacement, because it's a non-uniform force. Electrostatically, same thing. I have a charge. I put another little charge close by. I say it's the integral of f dot ds. So it's going to be the integral of f dot ds, and we learned that. I'm just going from f dot s, if you like, to integral of f dot ds. So now I'm back with book notes here. Just because you're going to see it in the book, so I want you to have an idea about it. So if electric field is uniform, then we can take this expression, that's that guy. Delta V is equal to minus the integral of E dot ds. And we can just do it. So E dot ds becomes E ds cosine of theta. And we know that the angle between these two guys, between the green dotted line and the purple field line, is 0. And the cosine of 0 is 1. So that becomes 1. So this goes E times ds. And E is constant, so I can take that out of my expression. And the integral of ds is just distance. So I've used calculus to prove what I started off by saying, oh, it's just the electric field multiplied by the displacement. So back here, it's just the, where is it? It's the, where did I put it? It's the electric field multiplied by the displacement. It's that guy, and basically I've just proved it from the general case. And you don't need to prove it, you just need to know it. Delta V equals minus ED. Delta U equals minus QED. And if it's varying, you do the integration with respect to the distance. If I do, that was potential difference in a uniform electric field. If I said the change in potential energy, when I move a test charge, it's the same thing. If the change in potential energy equals Q times the change in potential, which equals minus QED. Again, for a uniform field. If I'm not in line, it doesn't matter. I'm still going to turn around and say it's E dotted with S, which would give me that guy. So I can say my potential difference is equal to minus E times the integral of E dot ds, which is minus E dotted with S for a uniform field. And my change in potential energy is Q times my change in potential, which equals minus Q times E times S. And the only thing here is they're trying not to use D because they don't want to have DD for when they do the little bit of distance, because it's integral with respect to DD, which sounds a bit weird. But this is our old friend QED. It's just for a uniform field. And if you're going at 90 degrees to it, then this becomes the cosine of 90, and so this equals 0. So equipotential lines, no energy lost. Let's look at this problem. Consider a parallel plate capacitor that is used to create a uniform electric field. So I'm telling you what your E is. What is the potential difference between point A and point D? So I want my potential difference. So let's remember my potential energy equals my force times my distance, which equals my electric field times Q times my distance. So, and that is equal to that over Q, which equals, oh yeah, I remember that. It's E times D. And what is my electric field? My electric field is 6 newtons per coulomb. And what is my displacement? My displacement is 3 meters. That's going to be 18 joules per coulomb. Now, what am I trying to do here? And a joule per coulomb is a volt, so it's 18 volts. From a teaching point of view, I'm throwing a whole bunch of numbers at you, a whole bunch of distances, and I'm saying to you, which one are you going to pick? Are you going to pick the 6 times the 8, or the 6 times the 5, or the 6 times the 2, or the 6 times the 3, or the 6 times the 6? There's a whole bunch of numbers there to pick. So that's visualization. And what I could have done, let's see if I do it in the next example. Yeah. Yeah, it's just the same example. I'm just looking ahead to see if yes, I get there in the end. Okay. So in this case, consider a parallel plate capacitor that is used to create a uniform electric field. So E equals 11 newtons per coulomb. What's the potential difference between points A and B? So my potential difference is equal to E dotted with D, which equals 11 times my D. What is my D? I'm going to say my D is that. And it's going to be 4, which equals 44 joules per coulomb, which is a volt. And again, now I'm throwing even more numbers at you. You know, you could basically take that 4, you could take that 6, or you could try and do Pythagoras on it. Consider a parallel capacitor that is used to create a uniform field of 9 newtons per coulomb. What is the change in potential energy experienced by a 4 coulomb positive charge that is moving from? Oh, so now we have a charge that's moving. So I say, well, my change in potential energy is equal to QE dotted with D, which equals to QE times D times the cosine of the angle between. So my change in potential energy is equal to 4 times 9 times 3 times the cosine of 0, which equals 12 times 9 is 108. 108. And now I look and I say, well, let's have a look. It is a positive charge. So I have a positive charge going in the same direction as my electric field. It's like a boulder running downhill. That's going to be a negative sign. Joules per coulomb. Cool. Yep. Yep. And now the final level of complexity. I don't tell you the electric field. I say, consider a parallel capacitor that is used to create a uniform electric field. A 9-volt battery is connected between the plates. The plates have a gap of 2 meters. I'm asking you for the electric field. Electric field equals, remember that? dV by dx, volts per meter. Remember that from the previous chapter? Which equals, what's my delta V? 9 volts. What's my delta X? 2 meters. Which equals 4.5 volts per meter, which is, by the way, the same as which is the same as in newtons per coulomb. It's that guy. Yep. Cool. So I got it from the units, volts per meter. Volts per meter. I'll take something with volts and divide it by something with meters. But can you imagine I can put this together? I can give you, let's do another example here. So now I have plates. I'm going to put 12 volts. And I'm going to say that this is 8 meters. And then I'm going to have 2 coulomb positive, and I'm moving it from not 0 meters, not 1 meters, I'm going to go to 4 meters, and this is 8 meters. So I'm giving you a whole bunch of distances there. I want to know the change in potential energy. So I got this charge, I'm moving it from near the middle to near the edge in this thing. Let's think about the visual analogy. That's like I have a slope and I'm moving positive charge like up the slope, yeah? So I say my change in potential energy is equal to, and it's going to be Q E D, which equals, my Q is +2 times my E. My electric field is going in that direction, and my electric field is going to be 12 volts divided by 8 meters. And they're going to multiply it by the distance this thing moves through, which is 3 meters. And let's just look at signs for a minute. I've got a positive charge that's going upwards, so that should be a positive delta U. Yeah, agreed? So this is going to be 24 divided by 8 is 3. 3 3s are 9. 9 joules. Yeah. That's me throwing everything at you. That's me maximally trying to confuse you. I don't give you the electric field, I give you the voltage, but I give you the voltage for the parallel plate capacitors. Then you got to give you the voltage difference for the parallel plate capacitors. So from that you have to make the electric field up for the parallel plate capacitors. Then you say, well, it's a uniform electric field, but it's only this little bit of displacement I'm interested in. So you got a lot of visualization, a lot of building on that one. That's a kind of classic problem. So for these next bits, all I need to know is the equations. But I want you to go through it. I want to explain it. If you can understand where it comes from, you remember the equations because they make sense. So for this one, we have a mother charge here at the bottom, and we have a little point of interest, not a charge, but a point of interest. And it goes from A and it goes much further away to B. And what's happening here is, because it's a non-uniform field, as I go further away, my electric field decreases. And as I go further away, the angle between my little ds and my little electric field is changing for all points on here. So not only is my little bit of electric field changing, but also the angle between my displacement and the electric field is changing. So it's a bit of a mess. I say my change in potential, my potential difference is equal to minus E dot ds. And I can remember that E is equal to KEQ over R squared R hat. So I can substitute that in, and I get ds dotted with the R. Rather than the dotted with the E, because I've expanded the E, the vector bit is that R. So it's R dotted with ds. And R dot ds is R ds times the cosine of theta, and the magnitude of the little unit vector. The little unit vector is basically that guy pointing to wherever I'm interested in. The little unit vector is 1, and ds is ds, and cosine theta is cosine theta. But then I come over here and I do a little bit of a insight. I have ds, I have the little change in my distance from, my little change in my distance from, and I have an angle. And I know that dr equals ds cosine of the angle. So I can substitute that in. So E dot ds equals KEQ over R squared. And what I have is, rather than ds cosine theta, I have dr. So that guy becomes there. So I have this, my change in voltage is equal to minus the integral of E dot ds, which equals minus the integral of KEQ over R squared dr. I know how to do that. So I say I'm integrating now over all these little bits. I know how to do that. It's going to minus KEQ comes out because that's constant. And integral of 1 over R squared is minus 1 over R. And so I get, okay, it's going to be delta V KEQ 1 over R final. Let's call it R final minus 1 over R initial. Rather than A and B, we're going from A to B. So 1 over R final minus 1 over R initial. The path is irrelevant. What is the potential difference between 2 points? Point that is 3 meters to the north of a 2 coulomb positive, and a point that is 6 meters to the south. So I say, what do I say? I say that my, what is the change in potential difference? My delta V is equal to, what did we say it was? KEQ 1 over R final minus 1 over R initial. Okay? So delta V equals, leave KE alone, Q plus 2, 1 over 6. I think there should be a minus sign in there. Am I right? Let me go back. No, it's a positive sign. Sorry. So KEQ 1 over 6 minus 1 over 3, which equals KE times plus 2. And that will be 1 over 6 minus 2 over 6. Delta V is equal to KE times plus 2 times 1 over 6, which equals 0.33 KE. What would the units be? joules per coulomb or volts. Really better to be volts, but I'm going from a positive and I'm going downhill. Okay? Going from a positive and I'm going downhill. I'm going from, oh, sorry, excuse me, minus 6. 1 over 6 minus 2 over 6 is minus 1 over 6, which is minus. So I got the right sign. Okay? Cool. For time. 35 Coulomb charge is located at the origin. 35 Coulomb. What is the change in potential energy that experienced by a 2 Coulomb positive that moves from a point 0, 0, 1, 2, 3, 2 positive to a point 1, 2, 3, 4, 5, 6, 7. 2 positive. That's plus 3, that's minus 7. Notice, I'm not doing anything fancy with these guys. I am just taking them as position elements. Delta V is equal to, what is the change in potential energy? Delta V, delta U equals delta V times Q, which equals KE yes, KEQ 1 over R final minus 1 over R initial times my little charge. Yep. So here I said little q, because it's the only q in town, that was little q. But now I've got 2 charges to worry about, so I'm going to call this big Q and that little q. So I've got to be a bit careful about my q's. So delta U is equal to KE. My big Q is 35. My little q, let's take the little q. My little q is 3. 1 over 7. Don't worry about the negative sign. It's just 7 units difference minus 1 over 3. Delta U is equal to 9105 KE. I'm going to have 3 over 21 minus 7 over 21. The little q is there. Yeah. Yeah. So that's going to be 105 KE minus 4 over 21. So delta U is equal to 420 over 21 KE joules. Whatever that turns out to be. So, am I right? Is there a problem? Pardon? Oh. 2. 3 was, oh, bad Bonaquisti. Thank you. I'm rushing, so it's 70. Notice how when you rush, you mess up. So that's going to be, what, 70 over 21? No, it's going to be 4 times 70, 280, 21. And it's going to be a negative sign in there. Because I'm going downhill. Yeah. Cool. Suppose I want to find the potential at a point, not potential energy difference, not the potential difference, but the potential at a point. What I do is if you want to find the lowest potential energy, you've got to go to the bottom of the universe, but you don't know where it is. So you go to the top. And you go, as long as I'm sufficiently far enough away from all masses that they don't pull on me, I can't get any more potential energy. Because I get energy by moving against that force of gravity. So if I'm sufficiently far away from all masses that there's no pull, I'm at the top of the universe. And I'll count negatively. And that means that an upwards change is a positive change, even though the numbers are negative. You know, the top of the floor might be at minus 21 joules and the table might be at minus 19 joules. And that just means when I go like that, I get plus 2 joules difference. It works. Who cares if they're negative numbers? It's just numbers. Same thing goes with this. If I want to find the potential caused by a charge, then I've got to find the bottom, the bottom of that charge universe, and I can't find it. So I go to the top. I go sufficiently far away from any charges that there's no pull from those charges. I call that zero. So I can do the same thing. And what I can do is I can say, well, if I go from infinitely far away to that point of interest, what it means is that that infinitely far away point is infinity. And the nice thing is that goes away. So my delta V is equal to KEQ 1 over R final minus 1 over R initial. And my V is equal to KEQ 1 over R. So it's really nice. If you know one, you know the other. Notice that my potential falls off as an inverse, not an inverse square relationship. Let's have a quick look. Okay. What is the electric potential at a point 3 meters to the north of a plus 2 Coulomb charge? So here's my point, and this is 3 meters. My potential is equal to KEQ times 1 over R, which equals KE times 2 over 3, which equals 0.66 KE volts, joules per coulomb if you like, or volts. So it just falls out. Okay, suppose they have a bunch of charges. Well, you can just pick a point in space and you can just add them all together. You know, that's that point, that's that point, that's that point. Just add them all together. They're scalars. You don't even have to add vectorially. It's kind of nice. What's the potential energy due to a pair of charges? I've got one charge which is set up on a field. I bring the other charge to it. I'm doing work in bringing the other charge to it. I say, well, my potential energy is equal to the charge times the potential at that point. And my potential is equal to KEQ over R12. So I end up with this, the potential energy associated with, not the difference in, but the potential energy associated with those two charges is equal to KEQ1 times Q2 over the separation between them. If I have more than two charges, I just take into account all the bits. So there's that pairing and that pairing and that pairing. So I get KE Q1, Q2 over the separation between them, plus Q1, Q3 plus the separation between them, plus Q2, Q3 over the separation between them. So actually here is where, I said it was last chapter, but I guess it's again here, or it's this chapter, that my electric field is equal to minus dV by dx, which is saying the electric field is equal to the slope. You know, these are potential values, and there's my x, so there's my dV. There's my delta x. So my electric field is the slope of that relationship. If I have a cloud of charge and I want to find the potential at a given point due to that cloud of charge, I just do it for each little cube of charge. I'm going to talk about this next time, but I just want to talk about it. So, what this says is that if I have, forget about that one, just look at this one. I have a whole bunch of little bits of charge. Imagine it like a necklace. And for each one of them, the electric potential is the KE times that little bit of charge times that distance to the point of interest. That distance is Pythagoras, square root of x squared plus a squared. Every one of these is the same distance from my point of interest. So if I say that my total charge is equal to the integral of all the little bits of voltage, say my total voltage is equal to the integral of all the little bits of voltage, then it's basically the integral of KE dq over the square root of x squared plus a squared. Well, KE is a constant, and x squared is a constant, and a squared is a constant, so this equals KE over the square root of x squared plus a squared times the integral of dq. And the integral of dq is big Q, so this is KE big Q over the square root of k of x squared plus a squared. It looks complicated, but it's not. That's all you need to know on that one. Don't worry about these other things. And that's it. Okay. Sorry I ran over a bit.
What would you like us to know for the quiz?
Oh, quiz. For the quiz, I would like you to know. Whoa. I'd like you to know FE is equal to KEQQ over R squared. I'd like you to know that E is equal to KEQ over R squared. I'd like you to know that delta U is equal to, now let's go through this. Delta U is equal to E dotted with QED. I'd like you to know that delta V is equal to ED. I'd like you to know, what else shall we have? We can have delta V is equal to KEQ 1 over R final minus 1 over R initial. And delta U is equal to KEQQ 1 over R final minus 1 over R initial. You know, and and let's do, what did we say, what was that last one? One last one. Then I'll give it, U is equal to, I might as well do this one. U is equal to KE, it's Q1, Q2 over R12 plus Q2, Q3 over R23 plus Q1, Q3 over R13. Let's say that. I'll be happy with that. I'll be very happy with that. Okay. Take a picture of it. Tests. So I think it was 2 or 3 perfects, and I know that's cold comfort if you weren't getting perfect scores, but do an analysis to see what went wrong, what went right. Okay. If you think I misgraded something in terms of the answers there, but I've graded it as wrong, then by all means come and see me about it. If you think it deserves more partial credit, with due respect, that's my call. Okay, so if you want to tell me I'm mean, you know, join the line. But I try to be very fair across the board. Adam. Parker. Ian. Jose. Sergio. Leo. Noah. Austin. Justin, sorry, not Austin. Justin. Kevin. Ivan. Angel. Julissa. Andrew. Ryan. Darius. Anthony. Aaron. And Alejandro. I got some more little quizzes that people might want. Anthony, no answer today. Brian. No, Brian. Oh, he's got mine. Julissa's not here. Andrew. Kevin. Kevin. Noah.
Oh.
Aaron.
Wait. I think you said mine.
Andrew.
Yeah.
Yeah, there you go.
Thank you.
No Julissa today. Nawaf again. That's about it. Do I have lab with you guys?
Yes.
Oh, capacitors. No, not capacitors. Circuits. Oh, yeah, circuits.
Yeah.
That'll be long.
Yeah. It's a
Oh
long
my
lab.
god, see, I told you, bro.
It's a long lab. Yeah. But good. Long.